Here's 2010 Form B. So now we're on Form B, not Form the regular form, but Form B. Question number 3. And this is a question that deals with a bunch of different moving parts. So make sure to kind of follow along as best as possible. This is, by the way, is a calculator question. So make sure you guys have a calculator for this one. So it says, the figure above shows an above-ground swimming pool in the shape of a cylinder with a radius of 12 feet and a height of 4 feet. So notice that here's your radius, and then here's the height of the actual swimming pool. It says the pool contains 1,000 cubic feet of water at time t equals 0. So there's an initial condition. It already has 1,000 feet of water in it when we start. It says during the time interval from 0 to 12, water is being pumped into the pool at a rate P of t cubic feet per hour. So here's the table depicting that. So you guys can see that at 0 hours, water is not being pumped in. At 2 hours, it's being pumped in at a rate of 46 cubic feet per hour, so on and so forth. It says during the same time interval, water is leaking from the pool at a rate R of t in cubic feet per hour. And again, every time you see a formula like this on a calculator question, I would always put that directly into your calculator. So go ahead and do that now. Make sure when you guys do it, however, that you put parentheses everywhere that you possibly can think of. So for example, around that exponent, around that exponent, just because I didn't put them the first time and got the answer wrong. So make sure to put extra parentheses, more is better than less. And it says, note that the volume of a cylinder with the radius of r and height of h is given by this equation. So let's kind of summarize what we have so far before we get started. Let's get rid of that. There we go. So first things first, before we even get started, here's what we have. We have this table. The units are feet cubed per hour, and it's positive because we're adding water. The r of t function is also in feet cubed per hour, so these are both rates. This one is water entering the pool, this one is water leaking from the pool, so that's a negative function. And again, our initial volume over here is going to be, there we go. Our initial volume over here is going to be 1,000 feet cubed. That's how much water started in the pool to begin with. So, part A says, use a midpoint Riemann sum with 3 subintervals of equal length to approximate the total amount of water that was pumped into the pool during the time between 0 and 12 hours. Show the computations that lead to your answer. So, this is the table that helps us figure out how much water is being pumped into the pool. So let's go ahead and look over here at this table, and I kind of broke it down and only looked at the important pieces of the table. And you guys actually can't even see these colors very well, so let me see if I can highlight them a little bit better for us. Here I highlighted in green, this part, and then over here I highlighted in blue. They want 3 subintervals. So what I did was I broke this table up into 3 separate equal pieces, because it said it wanted 3 separate equal subintervals. And notice that they all have length 4. So from 0 to 4 is of length 4, 4 to 8 is of length 4, and 8 to 12 is also of length 4. So there's my 3 subintervals. Now obviously if this was a left Riemann sum or a right Riemann sum, we could do many more subintervals. But because they want the midpoint, and because we can't just randomly guess what the middle of each of these individual things is, we have to use subintervals where we already have a middle point. So in this red subinterval, notice that my middle would be 10, 62. In the green subinterval, notice that the middle is at 6, 57, and in the blue subinterval, notice that the middle is at 2, 46. So we have these midpoints of each subinterval already, and so that's why we break it up into 3, and that's why it's kind of set up the way that it is. So it says the integral from 0 to 12 of p of t dt, and notice that we have the approximation equal sign. It's not an exact equal because this is a table, not an equation. So it's not going to be exactly right, but it's approximately equal to 4, because they're all the same base, and then we just use the midpoints. So the midpoint of the first rectangle is 46, the midpoint of the second rectangle is 57, and the midpoint of the last rectangle is 62. And when you add all those together and multiply by 4, you get 660 feet cubed pumped in. So over the entire course of this timeline from 0 to 12, there were approximately 660 cubic feet of water pumped into the pool. And let's see how many points that is worth. That is worth 2 points. So you get 1 point for getting the correct midpoint sum, and you get another point for getting the correct answer. So just writing out the actual equation gets you 1 point, and then getting the correct answer gets you another point. All right, part B. Part B says calculate the total amount of water that leaked out of the pool during that same time interval. So remember that P of T gives us how much water is being added to the pool, and this function r of t gives us how much water is being taken out of the pool. So we already found our approximate integral of this table using the Riemann sum. Now let's go ahead and find the exact integral of this from 0 to 12. So let's use our calculators. Again, you need to 100% need to show the area. I'm sorry, not the area, what you're plugging into your calculator. If you just put the answer, they're not going to give you credit, okay? You have to show what you're putting into your calculator as well. If you don't put that, they will mark you off. So please make sure that, even if you have the correct answer, so please make sure you guys write this as well. So we're calculating the area under the curve of r of t, because I want to figure out how much water has leaked out of the pool in this time. So from 0 to 12 of r of t would be 225.594 feet cubed. And again, you should be able to just put that in your calculator really easily and get that answer. You get 1 point for writing the integral, and you get 1 point for writing the answer. Part C. It says, use the results from parts A and B to approximate the volume of the water in the pool at time t equals 12 hours and round your answer to the nearest cubic foot. So, notice that we have a couple things. We have an initial amount that was already in the pool. There are already 1,000 cubic feet in the pool. We have an amount that's pumped in. We just figured out that that's 660. And we have an amount that leaked out. We just figured out that that was 225.594. If you add and subtract those numbers together, you get 1,434 feet cubed. So that's how much water is in the pool approximately after the 12-hour day that you just had. And that is worth 1 point. So you get 1 point for getting that answered. Now, again, I'll kind of pause here, and before we move on to part D, I want you guys to understand and notice that these first three parts have not been very difficult. I mean, it took us like 7 minutes to talk about them and to get answers for them. So obviously that has not been very difficult. It would kind of signify, when that's true, it kind of signifies that a majority of the points are probably held in the last part, which is true here. We have 2 points, 2 points, and 1 point. Now, that's not bad. If you can get those first three, that's already 5 points. So 5 out of 9 is not bad at all. And let's see if we can get, some points, if not all of the ones from part D as well. But usually when that happens, when the first couple are easier, the last one definitely throws a bigger punch, I guess you could say. So it says, find the rate at which the volume of water in the pool is increasing at time t equals 8 hours. So first I want to identify, let me look over here, try and get some writing on this page for you guys. First, I want to identify what they're looking for. So it says, find the rate at which the volume of water in the pool is increasing. So a rate at which volume is increasing would be the rate that volume is increasing, that's dV dt. So we want to know what is dV dt. That's the first thing we want to know. And then the second thing says, how fast is the water level rising? So remember that water level would be like a height of the pool. So in other words, how fast is dH dt rising? Okay, so we also want to know dH dt. And it says include units of measure in both answers. So, hopefully when you're thinking about rates, they gave us that formula earlier for volume, so we're probably going to have to use that. Hopefully that kind of brings back memories of related rates, so we're going to have to use related rates. You'll notice that if we take the derivative immediately of this, we'll have too many variables that we don't know. So let's find dV dt first, and then we'll go ahead and take that derivative. So remember that the volume is increasing at the rate, well, let me back up. Let's go back up here to the top. We know that water is being pumped into the pool at a rate of P of T. So remember, this table up here is telling us how fast water is being pumped into the pool. Okay? This function tells us how fast water is leaving the pool. So if we want to know how fast the volume is changing, we can take this function, how fast, or we want to know how fast the volume is changing with respect to time. We can take this value, how fast it's being pumped into the pool at 8 hours, and subtract out the value of how fast it's leaking from the pool at 8 hours. So if we do that, we get dV dt is how fast it's entering the pool at 8 hours minus how fast it's leaving the pool at 8 hours. And again, from the table, you can just read that P of 8 is 60, and if you plug R of 8 into your calculator, you get 16.758, and when you subtract those, you get 43.242 feet cubed per hour. So let's just see how many points you get right off the bat for doing that. All right, so you get 1 point for finding v prime of 8. Okay, so if you can correctly figure that out, you get 1 point. So whoop-de-doo, I guess that's not that big of a deal. But, I mean, it is a big deal, but I was hoping it would give us more. So you get 1 point for getting that answer. Not bad. The next one says, how fast is the water level in the pool rising? So that's where we're going to kind of have to get into some related rate stuff. So if I can come over here to my second page, I'll just show you all at once. Now, I actually put up too much information, all right? So I'm actually going to cross some of this stuff out because some of it does not matter. Like this doesn't matter. I figured that out. If you really are lost, of course, you can go ahead and experiment with things. And I just kind of like experimented figuring out different things that I didn't actually need to. So unless you're really, really lost, try to stay on track to make sure you don't do extra work because obviously it would take me time to do that and it was not helpful at all. So try to stay on track as best as possible so you don't waste time that's limited. So here's our volume formula. If we take the derivative of it, and you'll notice that on the actual what is it called, rubric, that they actually plugged in 12 for R. And the reason is because R is a constant. The radius of the pool is not changing. The water level is, the height of the water is changing, but the radius is not changing because the pool is not getting bigger or smaller. So you'll notice in mine I actually took the entire derivative. So I had to use the product rule and the power rule and all that kind of stuff. And so it kind of ended up being a big mess. And it didn't need to be because look at this. dr dt is 0. So this entire piece right here is going to go away because dr dt is 0. Obviously, which means that it'll just go to 0. So I didn't actually have to do that whole product rule thing. You could have just plugged in 12s here for R and then realized that there was just one variable to deal with instead of 2. So you didn't actually have to use the product rule. I did, but you don't have to. And I'll show you in just a minute how they did it without using the product rule. So we just found out that dv dt was 43.242. Try not to round that answer because remember you are not allowed to round intermediate answers. So you literally just finished the previous part and got the entire thing and obviously you rounded it to 3 decimal places to write it on your paper, but don't round it here. So I notice that I actually do have this rounded. In my calculator though, I still have that entire value saved. So I just have it sitting there waiting for me to do something with it. I'm not deleting it, I'm not getting rid of it. So I wrote it here just to show you guys, but in my calculator I actually have the entire value that I just found in the last example actually written out on my calculator. So we have pi, this one went to 0 because the radius is not changing. The radius is 12, which is why I have 12 squared, and then I have dh dt, which is what I'm solving for. So the first thing I did was divided by pi. Again, this piece here is an approximation that I wrote down just to have something written on my paper, but in my calculator I still have the entire value written out. And then 12 squared is 144, and then when you divide by 144 you get an entire decimal, and now you can round it to write it on your paper. If you round these and you start just typing these numbers into your calculator, it might mess up your final answer, and they definitely will mark you off for that. So don't round these intermediate answers, you can only round final answers. So just be very, very careful about that. So the final answer was that the height was changing was 0.096, and notice that it's in feet per hour because height is not a cubic measure, it's just a linear measure. So that's feet per hour as opposed to feet cubed per hour like our volume was. Now, as far as points are concerned on this, we get lots of points for that. All right, so let's see how much of that we could have gotten. And I get that was a harder question, but you can get little points here and there. So make sure you guys do the best you can to try as much of it as you can. It says you get one equation for relating dv dt and dh dt. So just for taking the derivative, all right, you get 1 point for that. And again, notice that they just plugged in 12 here instead of keeping it as r. So when they took the derivative, it was just a super simple derivative. They did not have to do the product rule or anything like that. All right, you get another point for evaluating what dh dt is at t equals 8. Okay, and then last but not least, you get 1 point for the units, the correct units of feet cubed per hour for the first part and feet per hour for the second part. So again, evaluating at 8, we got 0.096, and then feet per hour here and feet cubed per hour there. So again, I understand that this entire thing was kind of a lot to handle, but pieces of it were definitely doable and things that hopefully, just by reading the context of the problem, you guys can start to understand.